Okay, right now I have everybody muted, but I think you should still be able to unmute yourself if you need to say something. Uh, Guys, I've never had anything like that happen to me. I thought all my settings were secure. And in the moment, I guess I froze. I wasn't exactly sure what button to hit to eliminate the trolls that were invading our session. Uh, I apologize. I'm not exactly sure that I could see or read everything they put in there, but I did file a report with Zoom, and I also sent a copy of that report to our tech support center at LBCC, and let's see what they say. So, you know what can I say? These things happen, and it's a new world out there, and hope it wasn't so disturbing that it'll kind of like, throw you off track. I'm going to try to keep on doing this, okay? I'm going to try to finish the lecture here. I need us to cover this next set of problems because they're important, and I want you to at least get as far as we can so you can take the quiz. I'll probably go back in and maybe, well, the quiz is scheduled to open at midnight tonight, but you have a few more days. So whatever we don't get to finish, I'll record it and post a message in there, okay? So here's what I'm going to do here. I'm going to open the chat again. And man, I just hope we can make this happen here. Okay, let me, hold on a second. Participants out, chat room on. Whew. Okay, let's come back here to our camera here. Oops, let me do this again. Put it on again here. Okay, so we were solving a problem where we had a mixture of acids, and in the first case we had a strong acid, nitric acid, with a weak one, nitrous acid, HNO2. And what we found was that in essence the solution behaves according to the contribution of hydrogen ions of the stronger acid. Okay, so whoever the strong acid is, that is who dominates. So this is, I think, the comment that I made here at the end. Some of these things that I have faded a little bit, so let me redo them again. So basically, remember, the system behaves as if only the strong acid is making a contribution. Okay? All right. So let's go ahead and tackle the second scenario. Okay? This is the one where you have two weak acids present. And by the way, if you have an old version of the slides, this value here for KA might be a little different. I was trying to use the one that's in the table in Top Hat or Tro. I don't know which one it is, but just a comment here is that whenever you're dealing with these values of ionization constants, just use the one they give you. Typically, the question itself will give you a value for Ka. The reason is that if you go through different tables, you're going to have different variations of what the Ka is, okay? All right, so let's make sure this is all working here. Okay, recording is going on, okay. So let me get my pen and let's solve this next one here. Okay, so now we have, in this case, we have two weak acids, all right? It might help to write out what the ionization equations are, just to help yourself out. So we have HClO, which is called hypochlorous acid, and that would have a ionization equilibrium that would look like this. And it tells us here that the Ka for that is 2.9 times 10 to the minus 8. The second one is our old friend HF, hydrofluoric acid. That one will also ionize with a Ka of 6.8 times 10 to the negative 4. Now, just like we discussed in the previous example, even though both of these are weak, you can see that the Ka of hydrofluoric acid is much larger, a good 4 orders of magnitude larger than the Ka of the HClO, the hypochlorous acid. So just like in the previous example, what we will propose is that the stronger, although in this case, we have to keep this in quotation marks, right? Quote unquote, stronger acid will dominate. So with that in mind, let's build our ice table for this exercise. Okay, here's my HF ionizing into those guys. I'm going to start out with a solution that, according to this, is 0.300 molar. And in this case, we're assuming that the other acid is not contributing significantly to the hydrogen ions in the solution. And so this becomes essentially a standard form of an ice table where you have the change in molarities, so that at equilibrium, you will have a concentration of unionized acid of 0.300 minus Y, and Y molar in each one of the other two species in here. So what we're going to do is solve the problem like we do with any other one of these problems. We're going to say that, in this case, the Ka is, okay, my video just froze here. Okay, hold on. Okay, there you go. Ka is given here as 6.8 times 10 to the minus 4. And in this case, that would be Y squared over the concentration of unionized acid. But as always, we'll start with our approximation method and say that this is pretty much the same as Y squared over 0.300, because we're going to say that the amount of ionization is minimal. I think my video just froze over here. Okay, let's see. Let me see if I can unpin. I suddenly got kicked out of the meeting here, and I don't know if everybody is still here. So let me go on the chat room here for a moment.
Professor, I think we're still here.
We're all here?
Yeah.
Okay, I got disconnected. I was afraid that I would not be able to rejoin. So hopefully we're here. Okay.
Yeah, the way Zoom is set up is if you get disconnected, then one of the students becomes the host for like a split second. So you get like a minute to like reconnect.
Yeah, the reason was that since I had locked the meeting, I was afraid that it wasn't gonna work out. So now, according to this, I think I'm still recording, so it may have paused briefly, but it says here it's recording, Nishan. I hope it all works, guys. All right, let me go back to my video here. Okay, so I think I left at some point where we're saying that we're gonna use the approximation here. Hopefully it got that far. And what's gonna happen then is we're gonna solve this, right? We're gonna solve for Y. So let's get our calculator back in here. And we have essentially 6.8 minus 4. And that is going to be times 0.3 And we're going to take the square root of that. And we get something that looks like 0.0148. But again, we only have two sig figs here. So we're going to put that as 1.4 times 10 to the minus 2. Okay. Now, all things being the same, this would be the concentration of hydrogen ions. But remember, we need to do our test, right? So let's make sure that this value that we obtained by approximation is okay. So 1.4 times 10 to the negative 2 divided by the initial concentration, or 0.300, times 100%. So that's, that didn't work out very well. That's not the number I had. Anyway, I had a different value over here, but that's all right. Let me try that again. I guess that's what we're getting. It's about 4.7%. Is that what you guys are getting also? I hope so. The point is that it's okay. We can save it. And so we have a valid value, a legit value for the concentration of hydrogen ions. So the pH essentially would be minus the log of 1.4 times 10 to the negative 2. Or a pH of 1.85. Two sixes here, 2 decimals on the pH reading. All right. Okay, so the moral of the story, I'm going to summarize it. Let me give a few seconds for you guys to write those things down if you need some more time. And the moral of the story essentially is, let me get myself organized over here, sorry. I'm gonna switch back over here. I'm gonna share a screen here and go back to our guess what? I don't have that in here. I thought I did. Sorry about that. So I guess what I was going to say was that there are a couple of points here to keep in mind. Number one, in any mixture of acids, the stronger or the strongest acid will dominate the pH landscape of the solution, all right? So we saw that both in the case where we had the, sorry, I can't find my paper that I had at first. Hold on a second. So that applies both in the case where we had the actual strong nitric acid with a weak acid, or this scenario where we had essentially two weak acids, but one of them with a significantly larger value of their Ka. Okay, so that's kind of like the take-home lesson here, is that you're gonna go by the pH that is dominated by the stronger or strongest of the acids in the mixture. And don't worry, we're not gonna make it to where you have two acids that are kind of like right next to each other. We typically don't play that kind of game with you guys, okay? So don't worry about that. Okay. Now, let me come back in here for a moment. Let me set this up for a moment, make sure I got the right file in here ready for us. Okay, I'm gonna start this. All right, so let me come back here to our Zoom. And let me take us to the PowerPoint again here. Okay, so this should be a slide that you have in there. And we're going to switch gears now and talk about bases. All right. We're going to talk about bases now. So this is an example of the ionization of ammonia. Notice that when we put ammonia in water, ammonia is a base. So if we use the definition of Arrhenius, it is a base because it produces hydroxide ions in solution, right? Let me look up here at our thing for writing. Let me get the highlighter. So the production of hydroxide ions basically means that it's going to be a base. It's also a base because according to Bronsted, it is taking a hydrogen from water, which in this case behaves as the acid. And in that sense, also it is a base. Okay? So just like we did with acids, we have an ionization constant for this equilibrium. We're going to represent it as Kb rather than Ka because it is a base. Notice again, products over the reactant with water not being included here. Just like we've discussed in other cases, the value of Kb represents the relative weight of the products side versus the reactants side. And so because of that, the larger the value of Kb, right? What that means is, let me erase this for a moment here. Erase that. The larger the value of Kb, that means that the bigger the top part of this fraction here is. And therefore, that means that the base is stronger, all right? Again, remember, when we say strength, it's relative. These are weak bases. We're just saying the greater the value of Kb, the less weak the base is. Now, when we solve problems with bases, we're going to use the same approach that we used before with acids. The difference is that in this case, what we're going to be solving for in our ice table is not going to be the concentration of hydrogen ions, but the concentration of hydroxide ions, okay? So don't forget about that. Once more, we have these tables, such as this one. This one is from the Tro book. The Top Hat book should have one also, where you have, again, on the left side, you have the bases. Notice that some of them are essentially the conjugate base ions of known acids. Many bases actually are compounds that have the nitrogen atom in there. These are all, in a way, kind of derivatives of ammonia, where one of the hydrogens in ammonia has been replaced, in this case, let's say, by a carbon. So let me get these things out of here. And you can see, for example, methylamine, you can see where it's almost as if you had ammonia, NH3, but you had replaced one of the hydrogens by this CH3 over here, which is essentially a carbon connected to the nitrogen and then 3 hydrogens on that carbon. Okay, so the way this works again is here is the list of Kb values, and this table is organized so that you have from greater or larger to smaller values. In other words, this is in decreasing strength of these bases. All right, so what we're going to do now is we're going to solve a problem. So we're going to go back to our paper. We're going to find out what is the pH of a solution that is 0.40 molar in ammonia. All right. So we're going to come back over here to our guy. Over here. Okay. And now we are going to solve for ammonia, if I can find it. So, got it. All right, so here we go. So again, what we're going to do is we're going to solve for ammonia. So let's write out what is the ionization of ammonia. So that'll be NH3. And with bases, sometimes we do have to write the water to remind ourselves of where things are going. So whereas with acids, we sometimes did a shortcut and we didn't write the plus H2O, we just simply put the dissociation. Here we're gonna do it. So here we have our products are gonna be the ammonium ion and the hydroxide ion. You know, if you want it to be correct, you should put the symbols, you know, AQ here. I'm trying to kind of save a little time here. Okay, so let's go ahead again and start with our initial conditions in molarity. This solution is set to be 0.40 molar in ammonia. And of course, at the initial stage, there is no ionization. Now here comes the change. Remember that I said that when we did acids, I would rather use not X, so it doesn't get confused with the times 10 to the something in our scientific notation. Well, tell you what I'm going to do here. I'm going to do something similar here. Since I was using the letter Y for acids, I'm just going to use the letter Z here for these guys. How about that? Or if you're Canadian, that'll be Z. So plus Z plus Z. All right. So that at equilibrium, our concentrations are going to be 0.40 minus Z, then Z in each one of these here. Hey guys, if you want to use X, that's fine. Don't worry, okay? Don't worry about it. It's okay. All right. So remember that the way this works here is we are looking at the ionization of a base. So what we are working with is Kb here, right? Which would be the ammonium ion concentration times the hydroxide ion concentration times, divided by the ammonia concentration. Don't forget, water is the solvent, so it doesn't get included here. And we had to look this up on the table, and I'm going to use a value that's kind of approximate. It's not exactly the one that I have in that table that I just showed you, but it's approximately 1.8 times 10 to the minus 5. This is from a table that we looked up, okay? Normally, in most cases, we're going to give you the value of Kb. So if this were a quiz or something, I would give you the value of the Kb. All right. So let's go ahead and do this. So we are saying that Kb, which equals 1.8 times 10 to the minus 5, equals the product of these two, so Z squared divided by 0.40 minus the change in concentration that happened. Once more, let's assume that given the small value of our K here, we should be able to do an approximation here and assume that the change in molarity of ammonia is fairly negligible, all right? And so we're going to say this is approximately Z squared over 0.40. So now we can solve for this, right? So this is going to be 1.8 minus 5 times 4. And we're going to take the square root of that. And we're going to get a value here for x. So 2.68328 blah, 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 times 10 to the third. We only have a limit of 2 sig figs here and 2 sig figs there. So we're going to abbreviate this. I'm sorry, round this to 2.7 times 10 to the minus 3. Now, this is what's very important. This is where you've got to be very careful, okay? Very careful with this. This is not the concentration of hydrogen ions. This is the concentration of hydroxide ions. So we cannot get the pH from there. So what we have is two approaches here. But first, let's do this. let's start out by testing our approximation to see if it was worthwhile. I mean, if it was, what's the word? Legit. So we had to see if 2.7 times 10 to the minus 3 divided by the initial concentration 0.40 times 100%. Let's see if that is less than 5%. So I have it in here. I'm going to divide by 0.4 times 100. And I'm getting basically 0.67%. So that means that our approximation is okay. We can use the value we obtained for X. Now, how do we get the pH? There are two ways you can go from here, okay? So here is one approach. Is to remember that we had the equilibrium constant that we call Kw, the ion product constant of water, equals to H plus times OH minus, and that equals 1.00 whatever times 10 to the minus 14. So I have this value. I have the value of the hydroxide ion, so I can say, well, the concentration of this guy is going to be 1.00 times 10 to the minus 14 divided by the molarity of hydroxide ions. So that's 1.00 times 10 to the minus 14 divided by 0.7 times 10 to the negative 3. Right? So 1 14 divided by 0.7 minus 3 equals 3.703 blah 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 times 10 to the negative 12. So let's take that to 12. Yes, it is a very small number because remember, this is a base. We already see that the molarity of the hydroxide ion is greater than 10 to the minus 7. And that means, therefore, that the concentration of hydrogen ions should be less than 10 to the minus 7 molar. We discussed this in our first lecture, remember? So what we're going to do now is we're going to calculate the pH from here. So pH would be minus the log of the molarity of hydrogen ions. Right? The log of this. Positive of that. Sorry, that was but essentially, let's do it again. But minus 12 and opposite. So that'd be 11.43. That would be our pH of the solution. Again, basic, because we have a base that is being ionized in here, all right? So that is one approach that you can use. The other approach you can use is you can remember, okay, this is our other approach. Is to remember that the pH of a solution plus the pOH equals 14. That is essentially taking minus the log of this equation here on both sides, and you end up with this equation. That means that the pH would be 14 minus the pOH. The pOH, of course, is minus the log of the concentration of hydroxide ions. In this case, that would be 14 minus negative 3. I'm supposed to put in here, sorry about that. Okay, so so 2.7 -3. We take the log of that, right? That would be 2.57. And of course, we had the negative here, but since we're taking a double negative, we're going to have the negative. This will be 2.57, and then I'm going to subtract that, which means that my pH is going to be this guy. That gives me 11. So notice that you have those two ways of solving the problem. And, you know, which one you choose is up to you, whatever you prefer. You can see that both of them gave us the same result. So it's okay to use either approach. Okay? All right. Let me make a quick stop here in case anybody has any questions. I think we're safe. You can unmute your phone and ask, your microphone and ask, or you can post a message here on the chat board. Hopefully we're safe now. By the way, when you guys joined, did it really request the password, or was the link already including the password in it? If anybody wants to answer that, would be great. No? Okay. All right. Well, let me put this out of the way then. Again, this will all be recorded, and like I did last time, I'll post also scans of these notes pages and use them also. I am starting to lose track of my own notes here. Okay, here we go. So let me go back to our PowerPoint here that we had before. Okay, so we did this. Let's see. I'm going to skip through this because we already did this on hand. Okay, now here's an interesting exercise that we're going to do. This is our next slide. Okay, let's say that I have an acid and I have its ionization expressed here, of course, with its corresponding value of Ka. And let's say that I know what that is. Now let's say that I take that conjugate in there, right? Remember that we have conjugates here. And let's say that I write the ionization equation for that conjugate. Don't forget, the ionization equation for a base is not the reverse of this one that I just wrote, all right? So what I'm asking is, what happens when I put that conjugate base of the acid in water by itself? Well, in that case, we have this equilibrium, and you recognize that as the equilibrium for a base, so it would have a Kb. Now, what happens if I were to come in and, let's say, add these two equations? All right, so what I'm going to see is, I'm going to see that, first of all, anything on the right will cancel out with anything on the left. So the conjugate base cancels out. The acid that started here got regenerated in the second equation. And so when we add these up, what we find is essentially the equilibrium for the auto ionization of water. And we know that that has a constant called Kw, the ion product constant of water. But if you remember from our discussion of equilibrium, what did we say happens when you add two equilibrium systems? What is the net equilibrium constant of that? Let me give you a few seconds to think about it. Yeah, exactly. When you add two systems in equilibrium, the net equilibrium constant is the product of the equilibrium constants of each one. Let's see how that works out. Let's write out Ka, right? That would be acid times conjugate base divided, hydrogen times conjugate base divided by the acid. And then Kb would be acid times hydroxide divided by the conjugate base. And once more, algebra here. We're going to cancel out the conjugate bases. We're going to cancel out the hydrogen, the unionized acid. And we end up with the product of hydrogen times hydroxide ions, which is essentially the same as Kw. In other words, let's say that I have a weak acid and its conjugate base. And let's say that the solution they gave me was the solution of the conjugate base in water, and they gave me the Kb value. How can I know what the value of Ka is? Well, I can get it from here. This equation told me, oh my gosh, I was about to use my my actual physical marker on my screen here. This tells me that the product of Ka times Kb equals the ion product of water. So if I want to know what Ka is, and I know the Kb of the base, I can find it by this relationship. Or if I have the Ka of the acid, and I need to find the Kb of the base, then I can use this relationship. So this is going to be very useful in solving other kinds of problems, all right? Such as the one that I'm going to do next. Well, let's go ahead and come back to our next problem here. Again, I don't know if this is in your slideshow or not, but I'm going to give you a piece of paper that has this in it. So no problem there. Okay. All right. So let's go back here. I'm going to switch over here back to our paper. So here's the same problem again. Let me see if I can zoom in a little bit. Yeah. Oops, too much. Yeah. Oop, too little. What? My fingers are just kind of like electric. All right. So we have here the slide. 0.135 molar solution of a weak base has a pH of 11.33. What is the Kb of that base? All right. So let's do this one. All right. So let's start out by inventing a formula. They don't tell us what the base is, so I'm just going to call it B, and I'm going to assume that it's kind of like just the conjugate base of something. And I'm going to ask what happens when I put it in water. Well, what I should get is I should have my base take a hydrogen and become Hb. And the water is going to give up a proton, so it keeps the electron and becomes hydroxide. So let's start out with our initial concentration, 0.135. And nothing happening here. Again, I'm going to use my variable here. I'm going to use Z or Z. Represents the change in these different species. And then at the end of the process, I'm going to end up with 0.135 minus Z, and then Z molar in each one of these guys, right? Now, in this case, they're telling us, right? They're telling us what the pH is. They're telling us that the pH equals 11.33. Now, the pH represents the concentration of hydrogen ions, which we don't have in this equilibrium here. So what we have is Z, which is the actual concentration of hydroxide ions. So we need to find what that is. And again, you can use either one of the approaches that we mentioned earlier. So for example, I can say that the pOH would be equal to 14 minus the pH, which is 11.33, right? I'm just basically bringing that in from here. And that gives me a value of 2.67. So to find the concentration of hydroxide ions, again, since POH is minus the log of the hydroxide ion concentration, then this would be 10 to the minus the POH, 10 to the minus 2.67. And again, be mindful of how your calculator works with these kinds of numbers here. And so in mine, it's going to give me a value of 2.1 times 10 to the negative 3 molar. You guys can try your calculator, see how that works. In some calculators, you put the exponent first and you click a key that has 10 to the minus that. Sometimes you just put it in sequence. So I'm going to let you guys get familiarized with how your calculator works, okay? Okay, but the question was, what is KB? Remember, this number we just found here is actually the Z in this ICE table here, right? Z or Z. So what I'm going to do now is, again, KB is going to be the concentration of the reconstituted acid times the concentration of hydroxide ions divided by the concentration of my base. So that is going to be, again, Z squared divided by 0.135 minus Z. And you know what? I can choose to do the approximation or not. It doesn't matter because I have the value of a Z, right? So KB would be 2.1 times 10 to the minus 3 squared divided by 0.135. If it's easier for you, you can write this in regular notation, right? So that would be, 0.0021. I mean, if it's easier for you to write it that way, it's all the same anyway. And I'm going to let you guys work on the math for that. And this will come up to a value of 3.3 times 10 to the negative 5. Let me throw in a follow-up. Well, let me give you a few moments to kind of process that. And then let me do this. Let me ask you a question. What is the Ka of this acid, HB? So remember, we said that if we know one of the two constants, we can find the value of the other one, because Ka should be Kw divided by Kb. So that's 1 point. I usually put 2 decimals here because remember, Kw is a constant. And so I don't care about its sig fix. I don't count its sig fix here. 10 to the negative 14 divided by Kb, which we said was 3.3 times 10 to the minus 5. All right, so let's see what that is. 1 to the minus 14 divided by 3.3 negative 5. And that gives me a value of 3.0 times 10 to the negative 10. Of course, remember what we said in the first class. If you're starting with a weak base, you're going to end up with a weak acid also. In this case, based on numbers we had seen before, actually it's based out, with other numbers that we've seen in that table before, we can tell that, amongst the bases, 2.1 times 3.3 times 10 to the minus 5, it's right in there in the middle of the pack with ammonia, somewhere in there. So that means that you would expect that its conjugate acid is going to be on the weak side of that scale. And that's what we have here. We have a very small value for the Ka of this acid. Okay? All right, so let me know if there's any questions. We have one more thing we're going to cover today. And once we do that, we are going to be done for the evening. Again, I apologize for the delays here. If you guys want to check out, I'll be recording the rest. But what I'm going to do now is I'm going to take a break. All right, I'm going to come back here. And what I'm going to do is I'm going to take a 10-minute break. So please don't disconnect yourself because, again, like I said, if you leave the meeting, you might not be able to get back in. So I'm going to put this on a pause in the recording. All right. I am going to stop my video here for a while. And we'll take a 10-minute break. And when that break is over, we'll come back. All right. So I'm going to pause the recording here for a moment. And in the meantime, if you have any questions, you can simply put them on the chat here for that. Okay. So here we go. I'm going to pause the recording for a moment and we'll see you in about 10 minutes. Okay, everybody, I think we're back, hopefully, and again, appreciate your patience and putting up with what we had to put up with, but hey, we're tough, we're resilient, and I appreciate all of that. Let me come back here to our video. Oh, there's me again. Okay, guys, well, we're about to finish here. Like I said, everything that you need for the quiz that's going to be opening tonight, we've already covered. So if you guys want to check out, that's fine. You can watch the rest of the video later. I realized we pretty much lost about 40 minutes of our time with that whole incident that happened earlier. I understand if you want to go. My plan was really not to have you here longer than 7, like a regular lecture time. And more, that's what I'm trying to do is kind of take us to a schedule that's similar to what we would have in school, with the added bonus that, you know, I will record these sessions. So if you are not able to join in at the time, you can see them later. And any other issues that you have, please don't hesitate to contact me, okay? And again, I want to say I'm sorry about what happened earlier tonight in our first part of our meeting, but it's nobody's fault except people who really, man, I wish they used their talents for something better in the world, right? But here's one thing I know, and I'll tell you this. We're going to talk about this later when we talk about thermodynamics after the spring break. And those of you who took Chem 1A with me, remember what I call Dr. DA's first law, right? There's nothing free in life. You pay now or you pay later, but you always pay. People who engage in that kind of activity to just intrude in other people's lives and try to disrupt other people's lives, you know, one of these days, they're going to have to pay back. So, I mean, how that'll happen and when, I mean, not up for me to decide, right? I do believe there's a higher power, but even if you don't share the same faith that I have, I think experience tells us that is true. Okay, enough pontificating here. Okay, let me go back to briefly to our lecture here, presentation. I'm sorry, to our PowerPoint, and we were here before, and I believe we saw this. Let's talk about polyprotic acids. A diprotic or triprotic acid, which are the more common ones, may yield more than one hydrogen ion per molecule. Now, here's the important thing is that when a polyprotic acid ionizes, it does so in a stepwise manner, okay? Very important, in a stepwise manner. In other words, they don't ionize all hydrogens at once. It's just one at a time, one proton at a time. So what you do is you write an ionization constant expression, or a Ka, for each ionization stage in the process. So consequently, when you are working with ice tables with polyprotic acids, you may have to do more than one equilibrium set, all right? Let me give you an example of one of these polyprotic acids. This is carbonic acid. So carbonic acid, H2CO3, is actually the substance that forms when carbon dioxide dissolves in water, all right? Or for example, if you were to take a straw and bubble your breath into water, it will turn the water acidic because, as you can see, carbonic acid, which is what is produced by CO2, is an acid. And there is its equilibrium constant, and we call it Ka1, all right? Now, the product of this ionization is the bicarbonate ion. The bicarbonate ion is also acidic, and so it can go through a second stage of ionization, where again, it produces hydrogen ions. The final product is the carbonate ion, which we can see over here at the bottom. And this one has a Ka2, that's what we call it. Typically, these have different values. So once more, like with acids and bases, we have these tables that show us the Ka values of different stages of ionization. Let's look at a couple of these for a moment, and please indulge me. The first one we have here is sulfuric acid. Hey, Dr. Dia, didn't we say that sulfuric acid is a strong acid? Well, it is, but sulfuric acid is diprotic. You can see where there's one hydrogen there and one hydrogen there, both of which can ionize. What happens is they don't do it at the same time. The first hydrogen to ionize does so completely. So sulfuric acid is a strong acid, but that only applies to the first hydrogen that ionizes. The second one has a Ka2 of 1.2 times 10 to the negative 2. So although amongst the weak acids, it'll be a fairly high value, it still makes the conjugate acid of sulfuric acid, which is HSO4 negative, a weak acid. I want you to take a quick look at these numbers here, if you can see them on your screen, and notice that as you go from Ka1, right, to Ka2, oops, my stylus is not working too well here, sorry about that. What do you notice about the values as you go from the first to the second to the third ionization in the case of the triprotic acids? Give you a few moments to think about it. So you notice that the pattern is that each successive value of the Ka is smaller and smaller. For example, phosphoric acid starts at a Ka1 of 7.5 times 10 to the negative 3. And then the second one, 6.2 times 10 to the minus 8. And the third one, 4.2 times 10 to the minus 13. Okay, so hopefully you were able to notice that. Now, let's solve a long problem here. And this will be our last activity of the evening. So I'm going to switch back to our handwritten notes here. Let me put them in place here. And let me stop sharing here. Let me take a moment to make sure that we are here. Okay. And hey, I'm going to say it again. Thank you guys. You guys are awesome. Thanks for just being so patient. And okay, I'm going to come back here to our handwritten notes. So I have here the same slide that you saw before. We're going to talk about oxalic acid, and it is a poisonous diprotic acid that's used in bleaching and cleaning agents. And let's say that we have a solution that we made, and that solution is 0.20 molar in quote-unquote oxalic acid. Remember, we now understand that when we say oxalic acid, we have to contend with all of these different ionization products, okay? Here are the two values we're going to use for Ka1 and Ka2, all right? And to solve this problem, we're going to have to break it up into parts. And so I need to find my notes. See where they are. Oh, here they are. Okay, so we're gonna have to treat this as a two-step process, okay? So step one is gonna be the ionization of just the pure oxalic acid. So that would be H2C2O4 ionizing into, of course, hydrogen ions and the conjugate base. Remember, the conjugate is different by only one hydrogen. So initially we start with HC2O4, and that should have a negative in it. I didn't bring this up, but when you looked at some of these acids, again, whenever you see these carbons here and oxygens, you have to, again, remember what we talked about carboxylic acids, where this hydrogen here represents the acidic one, and it's attached, most likely, in the majority of the cases, to one of the oxygen atoms, not to the carbon atom. Okay, so let's start our solution here by writing out our ice table. So it says here we start with a solution that's 0.20 molar. We start with no other ionization products yet. We're going to have a change, and I'm going to use the letter Y because it's an acid. Okay, so I'm going to have that change in there. So that at equilibrium, I'm going to have 0.20 minus Y, Y, and Y. It's sometimes good to draw a line here just to kind of like make us remember that we're doing some kind of like an equation here. Okay, so let's see what is Ka1. That would be hydrogen ion concentration times the conjugate base, which by the way is called hydrogen oxalate. Okay, so that's our formula. According to our values here, this should be 6.5 times -2. And we have the values here, so that would be Y squared minus Y. As usual, we will begin with our, approximation method and say that this is pretty much Y over 2 over 0.20. So we're going to solve here. And let me bring my calculator. And remember, this should be 6.5 to the -2. Square root of that gives us 0.11. Okay, you can tell without doing the test that that's not going to work, right? But just to humor you, let me do it. We're going to test here. So this would be 0.11 over 0.20 times 100%. Guys, this is more than half, right? So this is really a lot more than 5%, which means that we have to solve this problem. Exactly. By the quadratic method. Now, let me give you a little hint here. And again, as you practice more and more, you get kind of like, what would I say, hints, kind of ideas, kind of like little giveaways. For example, in this case, this value of Ka is not super small. Typically, a small Ka value runs less than 10 to the minus 3 or something like that. 10 to the minus 2 is a little bit higher. And the molarity that we started with here was not that high anyway. So it's kind of like, although I want you to go ahead and still try the approximation method, because you never know, just be aware that this is kind of a hint to let you know that you're probably going to have to solve this quadratically. So that means that we had to go back to our original formula here. I'm sorry, our original equation here. And we're going to have to do a quadratic solution to that. All right. I'm going to skip a few steps here. All right. And I'm going to show us what the final equation looks like. Y squared 6.5 times y. And I'm going to, like I said, like help a little bit here by saying this is minus 0.01. I took the liberty of skipping some of the math here and let you guys work that out. Again, don't forget the way this works is this would be in the format a x squared plus bx plus c equals 0. So that means that a equals 1, b would be this number here, and c would be not 0.013 but negative 0.013. Okay? So be careful with that sign there. So we now have to find solutions to this. Remember that the solution for y would be minus b plus or minus square root of squared minus 4ac by 2a. So if you put all those numbers in there, all right, what we're going to get is we're going to get two possible solutions. Y equals negative 0.15 or y equals 0. Again, I skipped all the math in here. Hopefully later on, if you want, you can work your way through it. This one here is not acceptable because y cannot be a negative molarity. So discard value. So we have y equals 0.086. So y equals 0.086 molar, and that is essentially the concentration of hydrogen ions. Oops, I'm sorry. This was kind of off screen. There you go. So y equals 0.086. That's the solution we arrived at quadratically. And again, I skipped a few steps in here. And so what you're going to have here is that's the concentration of H+. Now remember here, the question they're asking us is, what are the concentrations of all the species? So at this point, we could say that the remaining concentration of my original acid would be the initial concentration minus the change that happened, 0.086. And when you calculate that and round the numbers, you get 0.1. In other words, roughly a little bit more than half of what you started with. That's what's left of my initial acid, oxalic acid. All right. Don't forget, this concentration that we have here is also the concentration of the conjugate base. But remember, this conjugate base here is going to have to ionize further. I go through some further. I don't know what to use. Okay. And that's going to be the second step in our problems. Let me pause here for a moment in case anybody has any questions. You can either unmute yourself and ask, or you can put a message here on the chat room. Again, like I said, if it's about math, I kind of skip the steps there. You can check it later. But those numbers should be correct. So the important thing is that in the first step, we obtained the final equilibrium concentration of the unionized acid. All right. And now we have a concentration of hydrogen ions and a concentration of conjugate base that are now going to be part of the next step of equilibrium. Okay? So I'm just going to do it on another copy of the same slide. You guys may have a piece of paper. So now we're going to work with the second equilibrium here. All right? So let's see what that is. In the second step, remember, what was the conjugate base in our first equilibrium becomes the acid in this one. So this is HC2O4 ionizing into more hydrogen ions and the final ionization product, which is something we call oxalate ion. Let's work with our ice table. Careful. Remember, this guy here came from step 1. And we had said that the concentration of that ion was 0.086 molar. Oops, what happened here? My phone was, my wife says, running out of juice. Okay, so we had said that our concentration of that ion was now 0.086 molar, right? So that's what I'm going to use to start this second equilibrium here. All right? So this is going to begin at 0.086 molar. So is the hydrogen ion concentration, right? Because at this point, the first ionization step had resulted in a concentration of 0.086 molar hydrogen. The final ion is the one that's not present yet. So again, we're going to have a change here. We're going to use again the letter Y. And we're going to end up now with 0.086 minus Y molar in this hydrogen oxalate ion. 0.086 plus Y molar in hydrogen ions. And Y molar in oxalate ions. All right, so again, we're going to solve now this ice table, but this one is for the second ionization step. Again, which is hydrogen ions times the oxalate, the final ionization product, divided by our first ionization product, the hydrogen oxalate. Okay, we're being told that this has a value of 6.1. And according to our equation here, this is 0.086 times 0.086 minus. Once more, we start with the approximation method. And we're going to say that for all practical purposes, these changes in the molarities are going to be fairly negligible. So we end up with 0.086Y. Oh, what is that? Those two cancel out. Which means that from this simple approach here, Y equals 6.1 times 10 to the negative 5. Let's test our approximation, right? So 6.1 times 10 to the negative 5 divided by the initial concentration, 0.086. Let's see. 6.1 minus 5. Ooh, it's very, very, very small. 0.071%. So that means that our approximation is okay. So now, what we have to do is finish calculating our molarities. So we have the molarities here. We already have that the oxalic acid had a molarity of 0.1 more. That was called step 1. Now we have to find out what are the molarities of these other guys. What is the molarity of H+? Well, according to this, it should be 0.086, which was generated by the first step, minus this small value here, 10 to the minus 5. But think about it. This is going to the third decimal place. This begins in the fifth decimal. Essentially, there is no significant change in here. So this is pretty much 0.0 mole. You can say the same thing about our other ionization. That's supposed to be 0.0. I'm sorry. I made a mistake here. This would have been sorry, my mistake. This would be minus 6.1. But again, that difference is negligible, so this stays at 0.08 mole. And the last guy that we had here was the oxalate ion. And we said its concentration was 6.1 times 10 to the minus 5. Which, you notice, right? That is actually the value of Ka, 2. In other words, this is really numerically equal to the value of the constant. So what do we learn from this exercise? When you have a polyprotic acid, if the difference in value between the Ka1 and the Ka2 and any succeeding ones is sufficiently high, so it's like, let's say that it's 3 orders of magnitude different. Notice what happens. The molarities of the acid, the hydrogen ion, and the first ionization product, they all come from the first ionization step. The second ionization step contributed nothing to those molarities. And the molarity of the final ionization product is numerically the same as the ionization constant for that step. So if you have a problem like this one, where you're being asked to calculate the concentrations of all the species in a polyprotic acid, you really only need to do one ice table, the first one, because the first ice table is going to tell you how much of the unionized acid there is, what are the concentrations of hydrogen and the first ionization product, and then the final ionization product is going to be numerically the same as the value of Ka2, or the final ionization constant. So you don't really have to do this second table that we did here. I did it just to show you how it works. Okay, so let me give you a few moments to process that. Let me know if you have any questions. Again, once more, I may have skipped a couple of math steps here or there, but hopefully everybody's with me here. Cool. Okay, let me wrap it up by taking us again to our where are we? Here we go, to our PowerPoint. Okay, so this is the exercise we just did. So what I'm going to do is summarize these things here. Okay, this may not be on your slideshow, but it's exactly what I just said a few moments ago. If you have a polyprotic acid where the difference in value between the Ka1 and Kn2 is large, and I'm talking, 2 orders of magnitude or more, the concentration of hydrogen ions is determined mainly by the first ionization step. In other words, you don't need to do any further ice tables to find out the concentration of hydrogen ion. And if it's a diprotic acid, actually, the concentration of the first conjugate base is also going to be given by that first step, not by the second one. And the second thing that we learned is that the concentration of the final conjugate base, the final ionization product, is numerically in molarity is numerically equivalent to the Ka for that step. All right, so that gives you like a shortcut to all these things. And tell you what, I'm gonna move out of there now, come back here to my screen, and ladies and gentlemen, that's it. That's all I have for tonight. Again, just I can say it, thanks for sticking it out with us. We basically lost about 45 minutes because of that incident we had earlier. However, I'm very proud of you and thanks for staying. This recording will be available to you probably by tomorrow morning. So if you missed anything, I need a little more time because I'm gonna have to take that first video and edit it and then patch it with this one, just to remove the the stuff that we didn't like. Okay, so that's pretty much it all I have for today. Now remember that in our schedule, let me go back there again. Look at your schedule again. Where is it? There you go. Don't forget, in our schedule, we had that by tomorrow at midnight, right? You need to have taken quiz number 5. It's on Canvas. It's a multiple choice set of questions. And you need to upload your handwritten answers to the lab report, P13 and P14. I mean, unless you find a way of actually typing into it, some of you can do that. That's fine. Anyway, you're uploading a file into your lab report box there. Okay, you have until tomorrow at midnight to do that. I'm going to stick around for a few more minutes just in case anybody has questions about the lab itself or anything we discussed tonight. Okay, our next meeting will be on Tuesday. So let's see if we can prevent what happened tonight. So I will send you again, not a link, but I'm actually going to send you just the information with a password. So we'll make it a password protected meeting. And once we begin the meeting, in a few minutes into it, we'll probably lock it so that nobody else can come in. So please be punctual, okay? So that's what's due. And at some point tonight, a new quiz is gonna pop up here. And let's see. Oh, this doesn't work on the touch screen. So be mindful of that. Quiz number 6 is gonna be popping up sometime tonight, but you have until next week at midnight to do it. Also, over the weekend, the experiment P15 is going to show up, similar to the one you're doing for this week, and be mindful of that. Okay, so our goal is next week on Tuesday to finish chapter 15 of Top Hat. This is the unit on acids and bases, and begin the further study of solution equilibria with the topic of buffers. All right. Notice that I've moved the homework on this chapter 15 of Top Hat all the way to Friday of next week. So you have till midnight on Friday to do it. Then we'll be on a spring break. There's not going to be much, but hey, if you guys want to contact me, I'm not going anywhere. You know, we're staying safe at home. So please feel free to contact me by text or email if you have any questions over spring break. And I'm going to put a little thing later on Canvas, a little greeting and a little survey. I want to make sure that everybody's being able to connect with these things. And if you have any problems that I'm aware of. Okay, when we come back from spring break, that's right now the program is we will try to continue chapter 16 of Top Hat, and I'm going to have a dry lab session that night. So please plan on that being a longer session. You know, we'll have lecture, then we'll have a break, and then we'll have an actual short lab session to cover some of the dry lab that I'm going to post. Okay. Okay, let me come back here. Let me see if there are any questions here. Will I be uploading the lecture notes? So what I'm going to upload is both the video of this lecture today, but I had to kind of patch it together with the first part. And then I'm also going to load scans of all these notes that I took over the course of the lecture. Okay? So I'll try my best to get it done. I probably won't be able to get it. I don't know if I'll be able to get it done tonight, but we'll hopefully by tomorrow it'll be ready. I also had to do a lot of other stuff because I have my other class, my Chem 1A class. Believe it or not, I think you guys are probably a little bit ahead of the curve in terms of how I've been able to handle it. And but hey, we'll catch up and we'll be there. And push come to shove, many of your grades might not show up, I'm sorry to say, until spring break, because I might not be able to get to them until, you know, that week to finish grading all this stuff. But appreciate your efforts and hope you have a great weekend. I'm going to stick around a few more minutes, okay? Just in case anybody has any questions, just you know, unmute your microphone and let me know what you need, or alternatively put a message on your chat group here, whatever the chat board, whatever you call that. I'm sorry. All right. So if anybody has any questions, let me know. Okay, I know that typically questions sometimes come up not at the moment but later on, and I know that some of you are a little bit shy about asking. Okay, so let's see. I have a question from Rudy here. How do you factor out the Y? Did you mean in this last exercise that I did? Is that what you mean? You mean this one here? Sorry, Rudy's asking me questions, but he doesn't have a microphone. So, okay, so the question is, how do we factor out the Y? Well, because we said that since this is the concentration of hydrogen ions, which is this one here, times the concentration of oxide, which is Y, divided by the concentration of Hc2O4 negative, which is this one here. If we assume that this change here is negligible, we basically, you know, zero those out. And so we end up 0.086 times Y, 0.086 in the bottom. And so those cancel out. And it leaves you with a straight relationship that Y equals this same value over here, right? So again, the idea is that when you have a system like this, which equals a very small number here, what you're saying essentially is that this change in y is negligible. It's not significant, right? So, like I said, technically, you would have had to test it over here, but as you saw when we tested it, it's less than, it's less than 0.1%. It's very small. And that's because really at this point in time, this value is so small compared to the ionization constant for the first step that it drives everything to smaller values in here. Okay, cool. Okay, hey, I appreciate your questions and stuff. Yep, that's correct, Rick. So, thank you. It is small, so we drop it. Yes. Okay, let me see if anybody else has any other questions here. Wow, I'm kind of excited that several of you stay around. Again, the rest of you will be able to see the conference view. By the way, in spite of what happened earlier today, I don't want, to be a police, a law enforcement officer. I want you guys to feel free to communicate. So, once we know that everybody that's in here needs to be here, it helps if when you log in next time, which again, when I send you the link for the meeting, it's going to have a password. And when you log in, it should be possible for you when you start to sign in to put in the name that you're going to use. So please, if you don't mind using your real name, that'd be great, as opposed to nicknames or email addresses or things like that. I'm going to ask that just so that I can check the grid here and make sure that everybody who's on board is actually. Oh, Jennifer, you need to change that. I knew who you were. But it'll be very helpful if we can make sure that everybody who's in here belongs in here, and that way if something happens like last time, I can remove the intruders from our classroom here. Okay. Any other questions? Okay. Here's what I'm going to do though. I am going to stop the recording here. If anything else comes up, I will answer it in writing later on. Okay. So let me this here and go, and I am going to now stop